Here, I'm going to be talking about the idea of using spatial mode sorters as part of coronagraphs or astronomical instrumentation more generally. The LG mode sorter I'll be talking about here was originally invented within the context of optical fiber communications, which ostensibly doesn't seem to have much in common with the coronagraph, but there's more similarities than you might think. So in telecommunications, we've got multiple input source lasers, each modulated with its own channel of information. So each channel is spatially coherent with itself. It's in one well-defined spatial mode, but it's mutually incoherent with the other channels because they're modulated with independent channels of information. They all come from different sources, so there's no defined phase relationships between them. All these orthogonal spatial channels get launched into the same fiber core for fiber communications, or the same circular aperture if it's free space communications. Then those independent spatial channels of information get scrambled through the atmosphere or through the multimode fiber. Then the receiver has to be able to distinguish between those individual sources as it sees them through the circular aperture of the free space optics or the circular aperture of the fiber core. There might be 100 or so spatial and polarization channels all transmitting at once, so the contrast required is on the order of 10 to the 2. You want to pick off a single channel amongst a background of on order 100 other equally intense channels which share the same aperture. For a coronagraph, we've got a broadly similar scenario. In this case, we've got a relatively low number of sources, one very bright star, and maybe a small number of very faint companions. Let's say the separation between the sources is resolvable by the telescope, but no features of the individual sources themselves are resolvable, for simplicity. That is to say, each source is coherent with itself, its spatial mode is the PSF of the telescope, but there's no coherence between the objects. So a similar scenario to telecommunications, except the spatial mode basis is different. Telecoms is often things like Laguerre-Gaussian modes, whereas for astronomy, in the focal plane, our spatial basis is little offset quasi-spots. Equivalently, in the pupil plane, our basis are a set of tilted plane waves coming in from the different sources. Then, those sources get distorted through the atmosphere, through the optics of the instrument itself, or sometimes even through multimode fiber carrying light at the focal plane. And here, we've got a similar problem to telecommunications. How do we pick off a single source at the detector in the presence of aberrations and a strong background of other sources? The real key difference for exoplanet characterization is the obscene contrast. So whereas for telecommunications, you might be happy with an extinction of 1 part in 10 to the 2, for exoplanet characterization, you're looking for at least 1 part in 10 to the 4, but ideally as much as 10 to the 8, if you're looking for Earth-like planets. The principles I'll be discussing here are based on a new device called a Laguerre-Gaussian mode sorter, which is implemented using multiplane light conversion, MPLC. It's a device first used as the spatial multiplexer and demultiplexer in telecommunications. It's a device which can transform a beam into its Laguerre-Gaussian representation, which in the context of astronomical instrumentation means you can transform and filter light in a new way, not just transform back and forth pupil plane and focal plane using a Fourier transform. The LG mode sorter gives access to a new type of plane, the Laguerre-Gaussian plane, where spatial features such as circular symmetry are a natural part of that basis. I'll talk more about that in a second. It works like this. You feed in a beam. The light propagates through a cascade of phase masks, which map the beam onto a Cartesian grid of identical Gaussian spots, narrowing the Laguerre-Gaussian domain. Each spot contains a particular Laguerre-Gaussian spatial component which made up that original beam. So it's a spatial decomposition in the Laguerre-Gaussian basis. Traditionally, there's not been many options for doing spatial decompositions in optics. So Fourier spatial decomposition is an exception. It's a spatial decomposition that's of great practical use, but it's also easy to do experimentally. So, free space diffraction does the Fourier transform, and so does a lens. There's a whole field of Fourier optics which leverages this fact. Going back and forth from real space to Fourier space is experimentally straightforward, which means it can be used for optical signal processing, like we're seeing here. Transform into the Fourier domain, apply some spatial filtering function in that domain, a pinhole in this animation, pick off the Fourier terms you want, discard the ones you don't, and then Fourier transform back. The Laguerre-Gaussian modes are another common 2D spatial basis. Any field can be decomposed into its Laguerre-Gaussian representation, and the more modes you use, the more spatial components you include in the expansion, the more detail that can be represented. So just like in Fourier space, or just like in pixel space as well. You can represent a beam with Laguerre-Gaussian components, or Fourier components, or just with real space pixel components. The LG basis is a 2D basis defined in polar coordinates. There's a radial index, ρ, indicating the number of rings, and an azimuthal index, L, indicating the number of phase wraps around those rings. But unlike the Fourier domain, where you can use something like a lens to go back and forth between domains, there traditionally hasn't been a device that can do a similar operation for the LG domain. This is the schematic of a Hermite-Gaussian mode sorter. It will decompose a beam into its Hermite-Gaussian components. That is, it'll transform your beam into the Hermite-Gaussian domain. Some of the images I show will be of the HG mode sorter, and some will be of the LG, the Laguerre-Gaussian mode sorter. They're almost the same device. An LG mode sorter is just a HG mode sorter with two cylindrical lenses attached to the output. Looking at the schematic here, there's really not much to it. It's just a mirror and a set of phase masks. You feed in a spot from the left, you get a certain HG mode out on the right. And it works the same in reverse. You feed a HG mode in from the right, you get a spot out at a specific position on the left. So feed in a beam that's made of lots of different modes, like say an image, then you'll get an array of spots on the left, corresponding to the power in each of the Hermite-Gaussian modes which made up your image. On the left, there's a Cartesian grid of spots, and then on the right, there's a corresponding set of Hermite-Gaussian modes. The transformation it does is like so. The Cartesian position of each spot maps onto the HG mode with the corresponding Cartesian index, and then onto the corresponding LG mode if you want to add some cylindrical lenses. So if we shine light into each of the spots one at a time, this is an example of the measured optical field on the Laguerre-Gaussian mode side. So this is a 210 mode device implemented on a spatial light modulator. The phase masks for this particular 210 mode device look like this. It's got 7 planes. The phase masks are quite smooth, and if you were trying to reduce scatter, as would be important for a coronagraph, you could unwrap these phases to make something that's more like a refractive or reflective element rather than a phase wrap diffractive element. If you want a smoother design, you can increase the number of planes. So this is an extreme example of a simulation of a 101 plane device, all very closely spaced. And when you use so many planes, you're left with something that's effectively a smooth, adiabatic, three-dimensional refractive index profile. So it's got no sharp edges in the phase masks and only a tiny phase perturbation per plane. And this also naturally has high bandwidth. It acts more like a tapered fiber device, like a photonic lantern. Another implementation we've used is a 2D to 1D transform, which maps all the HG or LG modes onto a pseudo-slit. So that is a 1D array of identical Gaussian spots. This is a 45 mode device, which maps each HG mode on the 2D side, on the right, to a specific spot in the 1D array on the left. So all the spatial information is conserved for those 45 modes through that transformation, and it's all mapped onto a single line. It's a 2D to 1D transformation. That's what one of those look like in practice, implemented on a lithographically etched phase mask. So spots come in from a V-Griv array on the left, and then they're mapped to HG modes, 2D HG mode set on the right through 14 reflections off the phase mask. Okay, so the idea here is to use the LG mode sorter as a type of coronagraph, where we transform into the Laguerre-Gaussian domain, filter out the circularly symmetric components corresponding with the on-axis star, then transform back to the focal plane, or just stay in the Laguerre-Gaussian domain and analyze or interfere the spots there. The principles are kind of similar to a vortex coronagraph. For a vortex coronagraph, there's an on-axis star and let's say an off-axis companion. You apply a helical phase plate of even topological charge, so L equals 2, L equals 4, 6, 8, etc. Fourier transform it. The starlight on axis is blown up into that so-called ring of fire with a big dark null in the middle that has the diameter of the pupil. Meanwhile, the off-axis companion has a significant proportion of its power inside that null. Meaning if we remove the outer ring with a stop, we're left with just the companion. It's a type of circularly symmetric spatial filter. The operation performed removes the spatial components of the beam which are circularly symmetric on that phase mask. We could do a similar type of operation with a mode sorter. We start off in the focal plane, where we've got a scene like so, an on-axis star, and off-axis planet. Now we use an LG mode sorter to transform into the Laguerre-Gaussian domain. The circularly symmetric starlight, the on-axis starlight, gets distributed amongst the circularly symmetric LG modes. So that is the L equals 0 line through the center of the array. That's similar to our ring of fire for the Vortex coronagraph, except now it's a line of fire. Either side of that central line are the non-zero azimuthal index modes, which correspond with the off-axis light. Circularly symmetric parts of the beam, non-circularly symmetric parts of the beam. On-axis parts of the beam, off-axis parts of the beam. So if you block out the starlight by blocking the central line in the LG domain, then you can send it through another mode sorter to recombine them into a focused image. Or alternatively, if the objects are bright enough and you're not read noise limited, all those spots in the LG domain are identical diffraction limited Gaussian spots, so you could route them to spectrometers or interferometers directly. You don't necessarily have to reform an image if you don't want to, or you don't have to. If you're lucky, there might also be a spot which happens to have unusually large contrast even in the presence of real-world imperfections. I've illustrated these as focal plane devices like the Vortex coronagraph, but because the LG modes are their own Fourier transform, the amplitude of the LG mode decomposition is actually the same in both pupil and focal planes, so you could use it in either of those planes, or both. And there could be a few potential advantages to a mode sorter based coronagraph. In fact, it actually looks a lot like the mathematical description of an ideal coronagraph working at the fundamental limits, so a device that picks off the orthogonal modes of your pupil and separates them through cascading stages of interference. At the time of this paper, it wasn't clear how such a device could actually be implemented, but what it's describing is really just a mode sorter, sorting a set of orthogonal modes of the pupil. And I'm talking about Laguerre-Gaussian modes here, but you could also tweak the basis based on exactly what the PSF of your telescope is. It doesn't have to be Laguerre-Gaussian, you could also train it for a different set of orthogonal modes. Here in the black dotted line, I've got the theoretical maximum possible throughput a coronagraph could ever achieve for an unobstructed circular pupil. So it's a fundamental limit. It's just a measure of how much the off-axis field doesn't overlap with the on-axis field. So that's the power you could extract, the bit that isn't common to both. Right? So if you've got a star and a planet, let's say, in exactly the same spatial mode, then you can't separate them spatially because they're the same object. It's like if you had two horizontally polarized objects and you were trying to use a polarizer to filter one out but not the other. It's not going to work. Or two objects are exactly the same wavelength and trying to use a spectral filter to pick off one but not the other. Again, it doesn't really make sense. You can only pick off the component which isn't common to both the objects. So that ideal limit in black quantifies that overlap between the two objects for a circularly unobstructed pupil. A vortex coronagraph of charge 2 has a throughput indicated in red, pretty good at those small inner working angles. The simplest possible Laguerre-Gaussian mode sorter, supporting just 3 modes, would have a throughput like so. You could think of it a bit like a mode sorter that can detect on-axis and then one off-axis mode in X and one off-axis mode in Y. And that's about as simple as it gets. If you add more modes, it edges you closer to that fundamental limit at small angles. But after a few modes, you're pretty much at the limit. Adding modes is mostly about increasing field of view. You gain the ability to operate over a wider angle space. To filter off those really close objects, you really just need those lower order modes because there's not much tilt across your pupil for those objects. They're coming in almost on axis. The azimuthal index, plus or minus 1, will resolve most of that. Now again, I'm talking about using the Laguerre-Gaussian modes as a basis here. There's practical reasons why that's convenient. But if you wanted to train the multiplane light conversion system for a different basis, say the exact orthogonal spatial modes of your pupil, you could also do that, and then you would have the ideal coronagraph. And then you wouldn't just be near that black dotted line, you'd be on that black dotted line. Okay, so here we're looking at the total intensity of all modes in the pupil plane and the focal plane. On the left, we've got the modes, the mode sorter supports. In the middle, we've got what the sum of the intensities of those modes looks like in the pupil plane. And then on the right, we've got what the sum of those modes look like in the focal plane. For the simulation, I've chosen the waist parameter of the mode basis such that it fills the pupil as efficiently as possible. Starting off here, we've got just the fundamental mode and the L equals plus or minus 1 modes. So that's an N equals 3 mode sorter, supports 3 modes. As we add support for more modes, we get a slightly more uniform distribution across the pupil, but the change is more obvious at the focal plane, where adding more higher order LG modes allows us to resolve larger angles. So this illustration also makes the similarity between optical fiber communications and astronomy perhaps a little bit more obvious. In the pupil plane, that red circle indicates the aperture of the telescope, but it could just as well be the core clouding interface of a fiber. Like with the coupling into a fiber, the more modes it supports, the more efficiently you can couple into it, all other things being equal. We're talking about Laguerre-Gaussian modes here, but the more mathematically efficient mode basis would be the orthogonal modes of your pupil. So you could also train an MPLC device to sort the orthogonal modes of your pupil, whatever that pupil happens to be. Or perhaps you could use Bessel-like modes. They're at least theoretically more efficient than Laguerre-Gaussian modes for a circular aperture like this, because they're the modes that are more like the modes of a step index fiber rather than the graded index fiber. But it's also a pretty small theoretical gain, and we saw in the previous graphs that even the LG modes are already up pretty close to the theoretical limit. But importantly, the LG modes are better behaved in terms of MPLC device design. So there might theoretically be some other basis which is mathematically more efficient, but it might not necessarily be worth the trade-offs in terms of the actual practical implementation. Another potential advantage of the LG mode sorter is it operates in a basis which has the same geometry and symmetries as the Zernike modes. So they're both 2D bases in polar coordinates. And it's probably even more obvious by eye if we look at the degenerate representation of the LG modes as odd-even functions rather than plus or minus L functions. Right, so you can see that the two bases have basically the same features. And a consequence of that is that when you filter out certain LG modes to make your coronagraph, you're also attenuating the corresponding Zernike modes fairly directly. For a vortex coronagraph, to decrease sensitivity to aberrations, you keep the topological charge of the phase mask larger than the sum of the Zernike indices you want to suppress. So starting with charge equals 2, then we're only filtering out the piston term, the on-axis term, which is just as well because otherwise you wouldn't have a coronagraph. If you don't at least remove the on-axis term, then you're not removing the starlight. So in the simplest of scenarios, we've got maximum throughput at small angles, but maximum sensitivity to aberrations. Then, as you increase the topological charge to 4, you decrease sensitivity to tilt and to defocus. Increase the topological charge 6, you start to filter out astigmatism, coma, and spherical aberrations. Charge equals 8, and so forth. This square area of Zernikes of side length half the topological charge are attenuated. And the price you pay is you lose throughput at those inner working angles. For an LG coronagraph, the lowest order implementation blocks the L equals 0 line. It's similar to a charge 2 vortex coronagraph, except it's immune to circularly symmetric imperfections like focus, spherical aberrations, but also circularly symmetric obstructions of the pupil. Then, as we increase the order, we block more and more modes in the azimuthal direction, along that azimuthal axis. So if we block out L equals 1, that gives us insensitivity to tilt, but also to coma and all the higher order coma terms. If we block up to azimuthal index 2, we start to filter out astigmatism, but also higher order astigmatisms. Blocking up to L equals 3, we're blocking out trefoil and also all the higher order trefoil terms. The good thing here is, as opposed to a vortex coronagraph, where the charge equals 2, 4, 6, 8, etc., are physically different phase masks, which have to be fabricated and installed, the LG mode sorter would be a static device. It's just the width of that stop along the azimuthal axis that changes. And, if there's a specific aberration that causes issues, that could also be targeted more directly by just blocking out that specific LG mode. And there could also perhaps be some utility for wavefront detection as well. So say, for example, you've got too much light in the L equals 2 modes, then that implies you've got astigmatism. Too much L equals 1 means you're probably tilted or chromatic. We use that kind of feedback when we're coupling into multimode fibers sometimes to work out in what way we might be misaligned. Okay, so just to quickly go through here, I've got the throughput and contrast for vortex coronagraphs equal 2, 4, 6, and 8 in the presence of aberrations of increasing strength indicated with the dotted lines. So the inner working angle is 1.22 lambda on D, and then we've got these aberrations over the top of that. So in this first one, the aberration is tilt, and the strength of that aberration applied is the x-axis of these plots. So red dotted line is vortex coronagraph charge 2, green is charge 4, blue is charge 6, and magenta is charge 8. As the charge of the vortex coronagraph increases, the throughput goes down, but the contrast improves, and you get less sensitive to those tilt aberrations. In solid red, we've got the theoretical performance of the LG coronagraph in the simplest case, where we only block the L equals 0 row. It has better throughput than a charge 2 vortex coronagraph, but it's actually a little bit more sensitive to tilt aberrations in terms of contrast, but broadly similar performance. As we increase the order of the LG coronagraph, it behaves similarly to a vortex coronagraph of increasing charge. So we block out the L equals 1 rows, that acts like a vortex coronagraph of charge 4. Block up to L equals 2 rows, that acts like a vortex coronagraph of charge 6. Block up to L equals 3 rows, that acts like a vortex coronagraph of charge 8. Same trend for all these different orders. LG coronagraph has a bit better throughput, but a bit worse extinction for the LG coronagraph if you compare them on that basis. And it's a similar story for astigmatism, but also trefoil. All these purely azimuthal Zernikes that roughly correspond to the rho equals 0 LG modes, so the LG modes that look like just a single ring. The LG coronagraph and the vortex coronagraph are broadly similar for those kinds of aberrations. For defocus, spherical aberrations, and also circular obstructions, any type of imperfection that's circularly symmetric, it's theoretically completely immune. Contrast is theoretically perfect regardless of the strength of the aberration. It would just move light around left to right, not up down. So that line of fire would redistribute left to right, but it shouldn't leak up down. For coma, when you block L equals 1 on the coronagraph, you're also blocking all the coma terms across all the orders. So if we just go up one order and block the L equals 1 LG modes, you get a device with a throughput that's between a vortex coronagraph of charge 2 or 4, but a contrast that's better than any vortex coronagraph capable of working at it in an angle that close. So that solid green line on the throughput graph is between the throughput of a vortex coronagraph charge 2 and 4, but looking over at the contrast graph, it's got better tolerance to coma than any order of vortex coronagraph. Coma is treated basically the same as tilt as far as the LG coronagraph is concerned. So the real benefits I see here when compared to a vortex coronagraph in terms of aberrations are in the defocus and spherical type aberrations, coma, and the higher order aberrations of low N value. Okay, so that's it. Using the newly developed Laguerre-Gaussian mode sorter as a coronagraph could enable something which looks a lot like the theoretical description of an ideal coronagraph. And that's because the LG mode sorter is really about picking off orthogonal spatial components of a circular aperture as efficiently as possible, which could make it particularly well suited to this purpose. And then, as I said before, with the MPLC, you can also design different spatial bases for some specific pupil of your telescope. There's a lot of different tweaking options as well. You've also got the fact that the spots are generated as diffraction limited spots in the LG domain, which means you've also got options in terms of directly analyzing them or interfering them in that domain if you're not read noise limited.